Have you ever tried to get a cell signal while you're underwater? Yeah, it's pretty much impossible. And that's because radio waves, the backbone of our entire wireless world, they just don't travel well through water. So the deep sea, it needs a completely different way of communicating, using sound. But that comes with its own massive set of challenges. Today, we're going to dive into how scientists and engineers tackle these problems, not in the actual ocean, but right on a computer, by simulating this really ingenious routing protocol called vector-based forwarding. So here's our game plan for this explainer. We're going to start by really getting into why underwater networking is just so incredibly tough. Then we'll look at this clever solution called VBF. After that, we'll check out the tools used to model it. We'll even take a peek at the actual code that makes it all run. And then finally, we'll talk about why this kind of simulation is so absolutely critical for exploring the unknown. All right, first up, the underwater routing challenge. You can't just take the Wi-Fi router from your living room, drop it in the ocean, and expect it to work. It's not going to happen. The physics are completely different down there, which means the networking rules have to be completely rewritten from the ground up. To really set the scene here, what we're talking about are underwater sensor networks, or UWSNs. Just picture this: dozens, maybe even hundreds of small sensor nodes scattered all over the ocean floor, or maybe floating in the water column. And they're monitoring everything from volcanic activity to whale migration. They all need to talk to each other and to a central point on the surface, and they have to do it all using sound waves. Now, this is where it gets really crazy. Sound in water travels at about 1,500 meters per second. Now, that might sound fast, but get this. It's about 200,000 times slower than radio waves in the air. That creates a massive delay. On top of that, you have very, very little bandwidth, a ton of noise from stuff like ships and marine animals, and oh yeah, your nodes are constantly drifting around with the currents. And since they're all battery-powered, every single transmission has to be as efficient as possible. Your standard internet protocols, they just can't handle any of this. So how in the world do you get a message through all of that chaos? Well, that brings us to our next section. We're going to look at a protocol that was designed specifically for this insane environment: vector-based forwarding, or VBF. It is such a clever solution for a really, really complex problem. The whole idea behind VBF is actually brilliantly simple. Instead of making every single node figure out some complex, zigzagging route, VBF creates a virtual pipe, or a corridor, that points directly from the node sending the data, that's the source, to the node that's collecting it, which we call the sink. So how does this virtual pipe actually work in practice? Well, first, the source node establishes a direct line, or a vector, straight to the destination. Think of this as the dead center of our pipe. Then, the pipe itself is given a specific width. Now, when a packet needs to be sent, only the nodes that happen to be inside that virtual pipe are even allowed to participate. And of those eligible nodes, the ones that are closest to the center line of the pipe get the highest priority to forward the packet along. This whole system prevents a crazy storm of unnecessary transmissions, and it just guides the data super efficiently towards its goal. But, nothing's perfect, right? VBF has some pretty big trade-offs. On the plus side, it's super energy efficient and really robust. Since nodes don't need to keep track of complicated routing tables, they can just drift with the current, and the network just kind of adapts on the fly. It's fantastic for dense networks. But there's a catch. Every single node has to know its own location. And if the network is too sparse, if there just aren't enough nodes around, you might not have any nodes inside that pipe, which means the transmission just fails. So the width of that pipe becomes a really critical decision. Okay, this all sounds great in theory, but how do you actually test it? Deploying hundreds of these nodes in the real ocean is incredibly expensive and really, really difficult. And that's where simulation comes in. Welcome to the Digital Ocean Laboratory. The main tool for the job here is NS3, which is a super powerful network simulator that researchers use all over the world. But NS3 is really built for conventional networks on land. To make it speak underwater, we use this special add-on called AquaSim Next Generation. Think of AquaSim NG as the secret sauce. It adds all the necessary physics, like acoustic channels, propagation delays, and all that noise, turning NS3 into a seriously high-fidelity underwater network simulator. Now, this diagram might look a little complex at first, but it shows us exactly where our protocol, VBF, fits into the whole puzzle. Think of it like a layer cake. At the very bottom, you've got the physical layer. That's the water itself. On top of that, you have layers that handle how signals are sent and received. And right up near the top, in that AquaSim routing layer, that's where VBF lives. And this modular design is so important because it lets researchers easily swap in different routing protocols to see which one performs best, all without having to rebuild the entire simulation from scratch. Okay, so we've covered the problem, the theoretical solution, and the tools. Now for the really fun part. Let's pull back the curtain and take a look at the actual code that runs one of these simulations. We're going to break down a script called VBF.cc. Now, don't worry, you do not need to be a C++ expert for this part. We are not going to get bogged down in syntax. The goal here is to understand the logic, to see how all the concepts we've just talked about get translated into instructions that the simulator can actually understand. So, every simulation script starts by including its key ingredients, or its modules. The core module, that's what handles the simulation clock. The network module gives us the basic building blocks like nodes and packets. Mobility module lets us place our nodes in our 3D ocean space. The applications module is what generates the data traffic they're going to send. And of course, the star of the show, the AquaSim NG module, which gives us all those specialized underwater components. All right, next we have to set the scene with our parameters. So in this example, the simulation is going to run for 200 virtual seconds. We're creating a network with 200 sensor nodes and just one sink. Each node has an acoustic communication range of 100 meters, and they'll be sending these little 40-byte packets. These are the variables that define our virtual ocean environment. But out of all the code, this one single line is the most important one. This is where we tell the simulator to use VBAF. We give it the protocol name, and then we configure its key parameters. We set the width of that virtual pipe to 100 meters, and we set the target pause, the exact coordinates of our destination. This one line configures the entire routing logic for all 200 nodes. And this is the magic of simulation. A researcher could change that pipe width from 100 to, say, 50, run the test again, and immediately see how that one change impacts the network's performance. And you know, the best part is, you don't even need a supercomputer to do this anymore. Platforms like Afari and iPlayground have made running these complex simulations incredibly accessible. They basically give you a web browser-based environment where you can write, edit, and run these NS3 scripts, like the one we just saw, and even visualize the results, all without installing a single piece of software. It completely transforms learning into this hands-on lab experience. And this brings us to our final section. We've seen the what and the how, but let's talk about the why. Why is spending all this time creating a virtual ocean inside a computer so incredibly important? Well, it's all about modeling the inaccessible. The power of doing this is just immense. It lets researchers test a dozen different protocols in a single afternoon, a process that would take years and millions of dollars in the real world. It lets you create these perfect, repeatable conditions so you can isolate variables and truly understand why one approach works better than another. Ultimately, it gives us a window into these complex, hostile, and remote environments like the deep ocean that are otherwise almost impossible to study systematically. And that leaves us with a final thought to chew on. We've just walked through modeling a network in one of the most challenging environments on our planet. So the real question is, if we can accurately simulate this intricate dance of data packets deep beneath the waves, what other complex systems can we model? And what incredible new discoveries will these digital laboratories make possible in the future?